Very good morning to you all my dear students. So today class I am going to discuss about potential energy of bar magnet in a uniform magnetic field. So to derive this expression we should know one more thing, that is what is the torque acting on a dipole in magnetic field. So before that it was there in your syllabus, but now not there, that is torque acting on a dipole or a bar magnet in magnetic field is torque tau is equals to mb sin theta, which is very similar to torque acting on a dipole in an electric field, that is right. Torque tau is equals to what, ma? Pe sin theta, where P is electric dipole moment, m is magnetic dipole moment, B is magnetic field, E is electric field. So now I am going to derive the expression for potential energy of a bar magnet in a uniform magnetic field. So for this we should consider a uniform magnetic field. So if the lines of force are straight, parallel and equally spaced, we can say that it represents uniform magnetic field. In this I am placing a bar magnet north to south pole, and this is the magnetic length. As we know very well, the magnetic length is 2L. When you place a pole in a magnetic field at an angle theta, So now what is potential energy? If you place the bar magnet in a magnetic field, it starts to rotate. Suppose I want to rotate the bar magnet from perpendicular to an angle theta. We should do work done, right? That work done is stored in the form of potential energy. So we can simply define the definition as the amount of work done in rotating a dipole from where, this is the condition we consider, from perpendicular to any angle, means from perpendicular means theta to any angle, is stored in the form of magnetic potential energy. Is stored in which form? Of magnetic potential energy. So first we will rotate the dipole or the bar magnet through small angle, not from perpendicular to theta, right? So what we will do here? Let dw be the work done, in rotating. We can consider this as dipole or bar magnet, both remains same because that is also dipole na. In rotating an angle d theta, is it right? So now what you can write here? dw is equals to force into displacement. Here it expresses the force called rotational force, that is represented by tau. The angle is d theta. Already we proved what is tau. Tau is equals to torque acting on a dipole What is torque acting on a dipole? Torque tau is equals to what, ma? mb sin theta. So I can write this as dw is equals to mb sin theta into d theta. Consider this as equation number 1. Now what they are saying, that amount of work done in rotating a dipole from perpendicular to any angle means total work done in rotating dipole from 90 degrees to theta. Yes. How to get that? By integration. So we can write as total work done in rotating a dipole or bar magnet from where to where, ma? 90 degrees to theta. So we can write this as integration of dw is equals to integration of 90 to theta mb sin theta into d theta. As we know, what is integration of dw? What is integration of dw ma? W. Here mb is constant, mb into integration of 90 to theta sin theta into d theta. We know very well that integration of sin x into dx is equals to minus cos x. So, here what we got, integration of sin theta into d theta can be written as what? Minus cos theta. So, this version can be written as w is equals to mb into minus cos theta 90 to theta. Apply the limits. How to apply the limits? First, upper limit, that is minus work cos theta, minus of minus plus cos 90. Cos 90 is 0. What you can write? W is equals to minus mb cos theta. This work done is stored in the form of what? This work done is stored in the form of what ma? Potential energy. So, U is equals to minus mb cos theta. As we know very well, the dot product of two vectors a bar dot b bar is equals to ab cos theta. We can write minus mb cos theta as minus m bar dot b bar. So, this is the formula for potential energy of a bar magnet in a uniform magnetic field. Here there are different cases. For example, if the bar magnet is along the direction of, or the dipole moment is along the direction of magnetic field, means the magnetic moment and the magnetic field both are along same direction, then theta is equals to 0, then u is equals to what? Minus mb. This condition is called, means at this condition the bar magnet is in stable position. So, we can write that as what? Stable equilibrium. For example, if theta is equals to 90, means the bar magnet lies, the magnetic moment and magnetic field are perpendicular to each other, then cos 90 is 0. This condition is called what? 0 equilibrium. And the last condition, if the bar magnet lies along the direction, not opposite direction, means both are opposite direction, then u is equals to minus mb into minus 1, minus of minus plus, this condition is what? Unstable equilibrium. Okay. So, these are the conditions of potential energy of a bar magnet. So, here we consider the condition that when the work done is moving from, or the dipole is placed from 90 to theta, that is the condition. Generally, in problems point of view, they will ask the question as work done in rotating a dipole from theta 1 to theta 2, not from 90 to theta. So, we can apply the same condition, right? What is the condition ma? W is equals to plus mb into minus cos theta, theta 1 to theta 2. Maybe they will ask that the amount of work done in rotating dipole from 0 equilibrium to stable equilibrium or unstable to equilibrium to stable equilibrium. They won't give theta equals 180, but we know very well that if it is unstable, theta equals to 180, if it is stable, theta is equals to 0. Just apply the limits mb minus cos theta 2 minus of minus plus cos theta 1. So, work done in rotating dipole from theta 1 to theta 2 is equals to what? W is equals to mb into cos theta 1 minus cos theta 2. So, for problems point of view, this is very important. So, what we learned here? Potential energy of a bar magnet in a uniform magnetic field. So, what is potential energy? The amount of work done in rotating a dipole from perpendicular to any angle is stored in the form of potential energy. At first, we rotate the dipole through an angle d theta. For this, the work done is dw is equals to tau into d theta. What is torque on a dipole? Tau is equals to mb sin theta. So, dw is equals to mb sin theta into d theta. Total work done in rotating dipole from 90 to theta, we are applying the limits, and on integration we got w is equals to minus mb cos theta. This work done is stored in the form of potential energy. So, what the formula? U is equals to minus m bar dot p bar. Next question is what? Time period of oscillation of a bar magnet in uniform magnetic field. As we said already, when you place a bar magnet in a magnetic field, it experiences torque. Means what? It starts to rotate. For example, you are placing the bar magnet in a uniform magnetic field. Let us assume that this is a bar magnet or a magnetic needle. Yes, or north to south. What happens now? It experiences torque. What is the torque experiences? P mb sin theta. Yes. Now, there exists one more torque, restoring torque, which tries to make two bar magnet to come to its actual position. For example, I place this as bar magnet in a magnetic field. Now, what happens? It starts to rotate. It starts to rotate. If it starts to rotate, then one more force acting, that is called restoring torque, acting on it, it makes to try to bring this bar magnet to actual position. Again it experiences torque. Now what happens? What you observe here? This bar magnet is executing oscillations or not? It is repeating its motion. So what is the time period we are going to calculate? So first, when you place bar magnet, it experiences the torque, right? Torque acting on a magnet or a bar magnet, right? What is the torque acting on a bar magnet? Torque tau is equals to mb sin theta. So since the oscillations are made of very less magnitude, if theta is small, what we can write? This torque, this is called what? Deflecting torque is equals to what? mb theta. Now the restoring torque acts in opposite direction, means it makes the bar magnet to come to its actual position, that is tau r is equals to minus c theta. What is c? Torsional constant. It depends upon the nature of the medium. Right? What happens now? If it is at equilibrium, means the deflecting torque is equals to restoring torque, right? Sorry, tau is equals to c theta is for spring constant. For a body having moment of inertia, it is I alpha. I into alpha. What is I? I is called moment of inertia. Alpha is equals to what? Angular acceleration. Do not take this one because that is spring. I is called what? Moment of inertia, and alpha is equals to what? Angular acceleration. So if the bar magnet should be at rest, means at equilibrium, both should be equal or not? Should be equal and should be opposite in direction. I alpha is equals to minus mb theta. That implies alpha is equals to minus mb by I into theta. So consider this as equation number 1. So we already learnt a body executing SHM. If a body executing simple harmonic motion, means you know very well, to and fro motion of a body which repeat its motion after regular intervals of time along straight line is called what? Simple harmonic motion. angular acceleration is given by alpha is equals to minus omega square theta. Alpha is equals to what? Minus omega square theta. If you see these two equations, what are the two equations here we have? Comparing equation 1 and 2. Here alpha is angular acceleration, here also LH is same, theta and theta are same. What you can write, ma? Minus omega square is equals to minus mb by I. Minus minus cancel. What you got the equation? Omega is equals to root of mb by I. As we know, what is omega? Angular frequency. But what is our aim? To calculate time period of oscillation. So, we know that omega is equals to 2 pi f, right, that is equals to 2 pi by t. So, I want time period of oscillation. So, I can consider, if we want frequency you can consider this equation, if you want time period you can take this one. What you can write here? 2 pi by t is equals to root of mb by I. That implies t is equals to 2 pi into root of I by mb. So, this is the formula for time period of oscillation of a magnet in a uniform magnetic field. Here you should not get confused. What is I? It is not current. I is what? Moment of inertia. M is magnetic dipole moment and B is magnetic field. If you want frequency of oscillation, just as we very well known, F is equals to reciprocal of time period. Reciprocal, if you make it what? 1 by 2 pi into root of mb by I. So, this the equation for time period of oscillation of a magnet in magnetic field. What we done here? When you place a bar magnet in a magnetic field, it experiences torque. The torque is equals to mb sin theta. We assume that the oscillation, it is executing a system, theta is small, tau d is equals to mb theta. Now, when it starts to rotate, one more force acts on the body to make it to normal position. So, what that torque is called? What? Restoring torque. That restoring torque is opposite direction, that depends upon what? Moment of inertia of the body and angular acceleration. So, tau r is equals to minus I alpha. If the body is in equilibrium, both are equal. I alpha is equals to minus mb theta. From that, alpha is equals to what? Minus mb by I into theta. We know that if a body executing a system, angular acceleration equals to what? Alpha equals to minus omega square theta. Comparing these two equations, we got omega is equals to root of mb by I. We know that omega equals 2 pi f or 2 pi by t. We want 2 pi t. So, we got finally t is equals to 2 pi into root of I by mb. So, in this class we derived two derivations. One is potential energy of a magnet in a magnetic field. Next, time period of oscillation of a magnet in a magnetic field. And very important one is what? As like in electric field, we have also Gauss law in magnetic field. What is Gauss law in electrostatics? The total electric flux over a closed surface is equal to E dot ds is equals to what? Net charge enclosed by surface by 1 by epsilon naught times, right. So, here very simple, the total magnetic flux of a closed loop, the total magnetic flux of a closed loop is equal to what? 0. Why 0? If you take any closed loop, What is the reason for magnetic field? Pole strength, right? Yes. So, let us assume that the same formula as pole strength, E is replaced by B, ds is ds, net charge is net pole strength by epsilon is replaced by what? Nu naught. As we take that, if we take a bar magnet of different strengths, what happens? All having poles, because monopoles cannot exist. Monopoles cannot exist. What is the net pole strength of this bar magnet? Both having same pole strength but in opposite direction. This also both having same pole strength. This also having same. So what happens now? The net pole strength is 0. Then magnetic field also, magnetic flux also 0. So the net magnetic flux over a closed surface, instead of total we can say, because there is no magnetic flux, we can say that the net magnetic flux of a closed loop is equal to what? 0. This is what? Gauss law in magnetism. So this is important statement for 1 mark. You can write and explain what is Gauss law in magnetism. What is that? The total magnetic flux or net magnetic flux over a closed surface is equal to what, ma? 0. Clear? Yes. Thank you.